Okay. Like without further ado, let's get started. I think this is getting more and more important. Um, like our motivation is that our model is getting like super large right now. This is actually a pretty dated figure, but like a lot of slides use this. We've witnessed a lot of like improvements of our model sizes from 2017, the transformer architecture, to right now, like the 2021, there's like the GPT-3 model with 170 billion parameters. But this is actually from 2021, but right now we are at 2024 right now, and there's like models that are larger than GPT-3. There, for example, there's like the 540 billion parameter model came out from Google. So our models are getting larger and larger, but we don't have that much like compute resources. So that's why I think this topic is getting more and more important. How can we train small models or efficiently train these large models without that many computational resources? Um, like to be more practical, how much memory do we need to train or perform inference on these models? For example, if you want to train the T511 billion model, inference memory it requires is 176 gigabytes. If you want to perform inference on the OPT 66 billion parameter model, the inference memory you would need is roughly 1,000 gigabytes, and like the A100s are like 80 gigabytes, so you need a lot of A100s in order to perform simple like full precision inference. And this is getting like larger and larger. I would expect the models getting even more larger like three years from now. So like training fine-tuning can takes 8 times as much memory as this. So you can see that it's kind of like a very huge memory requirement for training and performing inference on these very large models. And this makes the cost of accessing these large models prohibitively large. So this is kind of the motivation. Okay.
What's the main component used for the inference memory here? It's mostly model weights.
I would get to that. That's a very good question. I will get to that in like a few slides, I think. So the topics today are mostly 2 parts. The first part I will talk about distributed training. The second part I will talk about compression. I think I will only cover quantization and probably distillation depending on how fast I can go. But first, as you can see, the topics today versus distributed training is about training large models on multiple GPUs. Like how can we train these large models on multiple GPUs? How do we deploy them? And secondly, how can we compress these large models into like small models or like without that many performance drop? So let's get to the distributed training part. So it's about training large models on multiple GPUs, as I've just said. Here's an overview of the methods I'm going to be covering today. First part is called data parallelism. It's about splitting data into multiple GPUs, but keeping the models the same as in the other GPUs. So here, this is kind of an illustrative figure right here. Green, blue, and yellow ones are illustrated different GPUs. The second part, I'm going to talk about pipeline parallelism, which splits the model but not the data into, for example, here you have like model 3 layers, L1, L2, and L3, and you split the first layer into GPU1, split the second layer into GPU2, and split the third layer into GPU. I would not cover this in too much details, but if you have any questions, please feel free to ask me. Yeah, let's head to data parallelism first. So the first part is kind of intuitive here. We shard the data. There's like the full data set. There's a green part, a yellow part, and a blue part. And we shard this data into the 3 different GPUs. This is straightforward, right? But how to train this model? Because since we have sharded the full data set into 3 different small data sets, and we are actually performing batch training on these small data sets rather than the full data sets. So we kind of need to aggregate the gradients. After we perform like a full forward pass on each of the GPUs, we get the local gradients of in each local GPU, GPU1, 2, and 3, and we aggregate them into a parameter server that's implemented. Also, there's a language model there. I will explain why there's a language model there, but right now all you need to know is that you need to aggregate the local gradients and perform like an aggregation to get the whole model gradients of the 3 different parts. Then the parameter server performs the gradient update. and actually distributes back the weights that after the updates and distributed back to each of the different GPUs. In practice, the parameter server is often the first GPU. So that's why there's a language model needed there in the parameter server, because you need to perform a full backward pass on the parameter server. And a full gradient update on the parameter server as well. So you can kind of duplicate the weights and distribute it to the first, second, and third GPU. As I just said, the parameter server is often the first GPU in practice, but you can actually set it to be any GPU that you want when you're doing your distributed training yourself. There's like a parameter that you can set it, and you can actually set it on any GPU that you want. You can also set it to an idle GPU, but I think that's not the most resource efficient way to do that. Yeah, this is just the pipeline of how do you do this data parallelism. Very, very simple, right? So first you do the data sharding, you split the data into multiple small chunks, distribute them into multiple small GPUs, and you perform the gradient aggregation, like you get the local gradients of each small GPU, aggregate them into like a parameter server, which is often the first GPU, and you update the weights at the parameter server, and then you duplicate the weights into all the small GPUs. This is very straightforward pipeline. Okay.
Is there anything you can share that this is for how often we want to do gradient aggregation and update step 2 and step 3, and then if you do it too frequently, it might really slow down our training, but if you do it too late, it might be too late.
I think the bottleneck here is not like when do you want to do the gradient aggregation, it's more about like how large your GPU size is. In practice, the case is that you want to use the largest size possible for each small GPU so that you can use a very large batch of training. So the batch size is actually, like, if you distribute the 3 small batch sizes, the total batch size that you're performing is actually the aggregation of the 3 small batch sizes. So like to be more concrete here, if you have 8 examples in the first GPU, 8 examples in the second, 8 examples in the third, the total batch size that you're using is actually 24 because you're actually aggregating the 3 gradients of the small batches. I think the bottleneck is the 8 here. You cannot increase the 8 because you're constrained by the size of the GPU here. So if you want to use it yourself, it's also very, very simple. You actually initialize your model with port distributed. This is just, I think, 1 line of code, and you make your model like distributed data parallel. And when you want to launch your script, you first right here, you specify which GPUs that are available. Here, this is 0, 1, meaning only the first and the second GPU are available. Then you call PyTorch distributed launch. Here, the nproc per node is the total number of GPUs to use. Sometimes there's like multi-node training, like there's like multiple GPU machines. Here you can set that too, but I will not cover that because it's not, at least in the computational resources we have right now, it's not very difficult. Maybe like if you go to industry, you will do this. But right now, I'm only talking about single node training, which is you have like a single machine and all the GPUs are on it. And this only works if the data set is too large. But like the question is that what if the model is too large? I've illustrated you are only starting the data, but you're duplicating the model several times. So you're actually paying a tax on the model sizes by duplicating it into multiple GPUs. But what if the model is too large? So here, the pipeline parallelism is kind of like a solution to what if the model size is very, very large and you need to start it into different GPUs. Here, in this case, you're not starting the data because here, as illustrated here, the data is a single one. You're not like splitting the data in any way. You're only splitting the model here. This is also often called model parallelism, but it's actually like a larger class that includes other different techniques. But here, the terminology for this is just pipeline parallelism. This is also like a very nice figure illustrating how we're doing this. Here we have a machine learning model with different like four different layers, and you kind of split the different layers into like the first GPU. So you split the first layer into the first GPU, split the second layer into the second GPU, and you split the last layer into like the edge. Very sweet. But okay.
Besides, for the clarity of the class, here the x-axis is time, right?
Yeah, time. So you first pass the data into the first GPU, get the result, pass the data into the second GPU, second layer. This is just like a standard transformer. You cannot pass the data into the second layer before you get the results of the first layer. There's no workaround about that.
And why is it that sometimes these splits are, sometimes you have 3 circles in a column, sometimes you have 2.
That's just for illustrational purposes. But imagine if you have like a large number of neurons in the first layer, like a smaller number of neurons in the second layer. You split the first layer. So this is not split evenly. This is just to illustrate. You can also split it. Okay.
When you say pass the results to the next layer, you're talking about the activations.
Yeah, the activations. So you first get the results, outputs. If a copy and paste outputs, you pass the outputs into the second layer.
Like the different phase like would require different time to processing the input. So like there must be some latency, right?
So in practice, you can have a very fine-grained control of how do you want to split your data, how do you want to split your model. Maybe the first 2 layers are very small, so you want to split the first 2 layers in GPU1. So you can have like a control of how do you want to split. It's not like you can only put the first layer in GPU1. It depends on your sizes of the GPU, obviously. And say, for example, in standard transformers, every layer is the same. So the most common practices is that if you have like a 12-layer transformer and you have 4 GPUs, each GPU would have like 3 layers. This is like an even distribution, but you can distribute it anyway.
I think there is one implicit assumption or implicit issue here is that it is important to also pay attention to what layers of a transformer are splittable into parallel processes, like maybe like processing different heads of a single attention layer can be done in parallel, but maybe one MLP layer cannot be done in parallel across multiple cores.
That is true. Right now, what I'm talking about, for example, in transformers, you're kind of using like each transformer block. So by saying transformer layer, actually what I mean is transformer block consisting of the multi-head attention layer and the MLP feed-forward network. The 2 together consists of makes a transformer block, and you put the block into this GPU. But certainly, if this is not like if it's parallelizable, everything can put into one single GPU. If it's not parallelizable, you need to do it sequentially. You cannot put it like you can actually split. So here is like a naive implementation of the pipeline parallelism. So you imagine you have 4 transformer blocks, or in this case layers, and you need to form like forward. The F means forward pass, the B means backward pass. You need to first pass the data into the first forward layer right here, then pass the data into the second forward layer, then pass the data into the second and the third, and you need to comport the backward pass as follows. So here, this is the 4 GPUs, and this is on the x-axis is the time. And when there's like a shaded area, it means that the GPU right there is being used by the certain forward or backward passes. So here, this is the illustration of the forward pass, the full 1 forward pass, forward backward pass. So you first pass the data using the first GPU with the first forward pass. Then for the second GPU, you do the second forward pass. On the third GPU, you do the third forward pass. And like obviously, you can see that many times when you are idle, a lot of the time that the GPUs are not being utilized here. It's just waiting for the previous forward pass. It's very simple here. When you're doing the first forward pass, the fourth GPU needs to wait for all the first 3 GPUs to complete their like forward passes in order to perform a computation. So a lot of the times are being wasted. This paper, G-Pipe here, proposes solution to this is that how you do this is you split like one large batch into like several mini batches. So for example, if you have like a 32 like a batch, you split it into 4 mini batches, each consists of 8 examples. And you don't need to wait, like the second GPU does not need to wait for the first 32 data examples to be finished to perform the second forward pass. It only needs to wait for the first 8 one to finish, and you can compute the 8th one. So this is actually making use of the parallelism in transformer architecture, or even like in other architecture, this is also the case. You're actually splitting the mini batches into the first 8, second 8, third 8, and the fourth 8 mini batches, and you perform the gradient aggregation. This is similar to how you perform gradient aggregation in the data parallelism. So you're kind of like combining the data parallelism and the model parallelism here. But here, all the data is all in the first mini batch here, and you're only splitting the batch into like very tiny batches. So you don't need to wait for the first full batch to be computed. Like you can see that if you do a very fine-grained one, you can do like 1 by 1. This is faster, but there's actually also a tax you need to pay here. This is the inter-GPU communication. So whenever you pass the data from one GPU to another GPU, there's like a latency between this. So it's not like if you want to split it into like 32 mini batches, each consisting of one single example, you get the fastest result. There's like a trade-off between the size of the batch and the time you need to perform for the inter-GPU communication. So this is how people solve this sort of idle problem in pipeline parallels.
Question. So in practice, identifying this optimal mini batch size, how is it done? Is it just done like with empirical analysis, or one can think about it?
You can actually do a lot of like experiments on this. This is a hyperparameter you can optimize, but in practice, people just use standard libraries, and they just put like a parameter into the calling the library, and you don't actually like optimize too much on this. I think so. It also depends on the actual GPUs are you using and the hardware you have. So it's not like standardizable. Like if you want to perform like a research on this. The pipeline parallelism, you can also use it by yourself. This is like just for example here, we have 2 feed-forward networks, fully connected layers. You pipeline right here on the line here, you pipeline the 2 together. And the 8 means that you are kind of splitting the chunks to 8 different small batches. This is the same as before. You are using 2 GPUs, distributed launch, 2 different GPUs, and you call the Python script that you're using. Okay.
In your code here and in your previous code, you're using the keyword node, which might not be clear to the class how a node is different than a GPU.
Oh, so here a node consists of multiple GPUs. A node is kind of like a machine. There's like multiple GPUs in a node. For example, I think you work with the Rockfish cluster, right? In Rockfish cluster, there's like different nodes. Each node consists of 8 GPUs, something like that. There's also like the distributed training I'm talking about today is only about you're doing distributed training within one node. But you can obviously do like distributed training within several nodes. There's multiple GPU machines and you do the distributed training across them. We're not talking about that today, but if you're interested in that, you can also talk to me, and there's not standardized libraries to do that. So it's not very hard to do. Today, I'm just giving you like a kind of like an overview of different methods. So to answer your question, where did all the memory that we use go? Like for example, if you have like a GPT-2 large model with 1.5 billion parameters, and it takes, like, if you only want to store the model, it takes only 3 gigabytes of memory if you're doing in like 16-bit. And so each parameter takes up 16 bits. This only takes about 3 gigabytes of memory. But training it requires more than 32 gigabytes of memory. So why do we need this much memory in order to train a model, which only takes about 3 gigabytes of memory to save? So in practice, most of the memories are actually occupied by the optimizer states. So we know that the Adam optimizer needs to store multiple copies of tensors of the size of the parameters. For example, you need to store the momentum and the velocity. Some memory are also occupied by the residual states. For example, there's like activations. After you compute, you need to kind of store the activations, buffers, and the fragmented memory. So the memory, like in like modern GPUs, you cannot use them densely. There's like after you reserve part of a memory, there's like part of the memory that's unused. So there's like fragmented memory that's unused, but it's also occupied by the model. So if you kind of do a more like a straightforward illustration of how much memory does the optimizer states require, so you can see the parameter only occupies like four squares. The gradient also occupies the same size of the parameters, but the optimizer states actually occupies a much larger. Here there's like 24 squares. This is roughly the same amount as in practice. The reason is that the optimizer states, even if you store the parameter and gradients in half precision, in like a lower bit precision, you still need to store the optimizer states in full precision. The reason I've actually checked yesterday, I think, is because if you want to compute the optimizer, like the Adam optimizer, requires a lot like a higher numerical precision than like the gradients and parameters. I don't know why is that, but this is what they explain in the paper. So as I've illustrated here, most of the GPUs are occupied by the green, which is optimizer states. Here like a total memory for a 7.5 billion model with using the Adam optimizer is 120 gigabytes each. So here each GPU needs to have like a 120 gigabytes in order to form this. So you can see that it's a very large number. So people posed a lot of ways to solve this, but mostly you need to kind of like do something on this optimizer states, because since you're like duplicating the model into 3 different GPUs, for example, in data parallelism, you need to store 3 copies of the full optimizer states. This is a huge waste of your memory. And what they propose is that you shard the optimizer states. It's very straightforward. You have 3 GPUs, so you can shard it evenly. You can also shard it unevenly, but in practice, people shard it mostly evenly. So here, instead of the full optimizer states, you only need to store like a sharded part of the optimizer states in this case. So the total memory for a 7.5 billion model with the Adam optimizer here is only 54.8 gigabytes. So each GPU, instead of the full 120 gigabytes, it reduces the number of like memory required in half. This is the most practical thing that people use right now, is that instead of doing this model, like when doing data parallelism, you don't split the model multiple times. Instead, you don't only save the parameter and the gradients, but you split the optimizer states as well. This is called the zero optimizer, and this is when you shard the optimizer states. This is called the stage 1 of the zero optimizer. Going to stage 2, you not only shard optimizer states, but you also shard the gradients. So after you shard the gradients, they can be computed by aggregation. So you are saving more memory by sharding the optimizer states. This is called the zero optimizer stage 2. And as you can see, you go from like over 50 gigabytes. Right now, you only need 47.9. This is a small decrease compared to the previous one, because right here there's only 3 GPUs. Imagine you have like 60 something GPUs. this will be a larger decrease. This is stage 3. You are charting everything. The total memory goes down to 41 gigabytes compared to the 49 gigabytes. You're still saving much more memory. Like this is a very, very practical number because I think the A6000 GPUs consists of roughly 40 gigabytes. So the more GPUs you have, the more you can save by charting these parameters and gradients. But I think if you want to try this yourself, I think there's standardized libraries to do this. The most practical one is the stage 1 of the zero optimizer because it charts most of the green parts and it's saving most of the memory for you. Any questions about the zero optimizer?
Yeah, I'm kind of confused here because like we are doing data parallel here, like we said before, like if we are doing data parallel, we have to like copy the same model in the multiple GPUs. But here we are also sharing parameters.
This is so the zero optimizer is not like so when you're going to data stage 3, you're not exactly doing data parallelism, you're doing a combination of data and model parallelism, since you're also charting the parameters as well.
So like how does it work in practical? Like there must be some interaction between the GPUs like to use the other parameters.
For example, for example, if the first two is the first 2 layers, you can put the first 2 layers in the first GPU, the third layer in the second GPU, and the fourth layer in the third GPU. This is exactly like the parallelism, pipeline parallelism. There's also other ways to do that, but it's more complicated, and I can refer you to some like readings about this. By the way, this gets asked a lot in like job interviews, so it's nice to keep that in mind. Okay.
So basically, so we are saving a lot of memory here. Is there a cost that we are paying by doing this?
We're always paying a cost when we're splitting anything by paying the cost at the inter-GPU connection. Because the like inter-GPU connection is the speed is super high. There's like a specialized area for doing these high speed computations in GPUs. But the if you're splitting it across multiple GPUs, you need to transmit the data from one GPU to another. This is a cost.
And earlier you mentioned that comment that the more GPUs you have, the more benefits. The benefit as in terms of memory size. Is it true that the more GPUs you have, you're also paying more cost for communication?
That is true, but in like modern large scale, I don't think our cluster has this, but most clusters has this high speed connection, even between nodes, between GPUs is certainly much more faster than like doing it on like our grids, I guess.
Right. So I guess
the specialized hardware.
That's true. I guess my question is more like, does the communication cost also increase or communication cost because you're really doing this kind of neighborhood communication? Maybe actually it remains low even when you increase the GPU size.
It increases. So like for example, if you're transmitting only 2 GPUs, you only need to transmit from GPU 1 to 2. But if you have like 60 GPUs, you need to transmit from 1 to 2, 1 to 3, just like a
all between
all. Yeah. Okay. So all of them needs to be connected, and this is a huge cost to pay. But it's nothing compared to the memory that's required. You get to save a lot of memory, especially when the size of the model is super large. Here's like a tutorial running Llama 2's 13 billion model. This is from King Hao from Chicago. I actually talked to him yesterday about this slide. This is like how do you do this in a very like if you want to do it yourself, you just write the trainer in your code. This is just standard copy paste trainer of the Llama 13 billion model. You prepare the zero optimizer configuration. Here, in this case, he's using stage 3. I don't know if you can see this slide, but here he's using stage 3. You launch it with a specialized library called DeepSpeed, and you just do the standard, like say, parameters you're using. For example, in classification here. And then you see that the GPU usage is kind of balanced between all the GPUs. Like this is when you inspect the GPU memory usage. This is roughly 50 gigabytes, and you're using 37 gigabytes each. It's kind of evenly split. But if you don't use this like distributed training, it's impossible to fit something like Llama to 13 billion into a single GPU of 50 gigabytes. It's impossible. I don't think there's any way to fit it in and perform training. Like yeah. So much about distributed training. Like, is there any questions here? Okay.
How can you do a case of like a network slash filter?
Well, that's very practical. Actually, I've actually worked on something like this. For example, in large scale distributed training, if one of the GPU goes down, everything goes down. So if you have like if you're training like a pre-training large, say 1 billion model on a 64 GPU machine, and one of the GPU goes down, everything just stops. So there's like people that actually babysit the entire training process. Yeah. So I feel like maybe the machine learning systems guys are working on some sort of fault tolerant distributed training frameworks that when one GPU is down, the other GPUs will like take over his job. But right now I don't think there's anything that does this. So it's very fragile, and there's like people babysitting it all the time. Yeah, is there any other questions about distributed training? Great. Now we can move to the next section, compression. This section is about how can we make these super large models smaller with like no to minimal performance drop. So here's an overview of the methods. I think I'm only going to like introduce the first two methods because the third method, I don't think it's very practical right now. People only use it for, I guess, research purposes. There's nothing that's deployed, or there's not this kind of framework that does it for you. But the first two is very practical. The first one is the most practical, called quantization. It stores or performs the computation on 4 or 8-bit integers instead of 16 or 32-bit floating point numbers. So instead of representing numbers with 32 bits, you're representing numbers with a much lower bit, so that it takes much less memory. This is the most practical way and most effective way of doing training inference of a large model. The second technique I'm going to introduce is called distillation. It's about training a small model, like the student model in this case, on the outputs of a large model. So you're actually using the output budgets of the teacher model of a large model to train a student model. It's kind of similar to like model ensembling. And we can actually distill between the same architecture to get some performance gains. Yeah, so mostly I will talk about quantization and distillation. These two techniques are the most practical, and there's also a lot of frameworks, libraries to do this for you, so you don't need to write it all yourself. So in order to understand what's quantization, we first need to understand like how is numbers represented in like modern computing systems. So here's an example of the 32-bit floating point number. This is also commonly called FP32. If you were used the training yourself, you can see the FP32, FP16. This is what FP32 means. This is you represent each number with 32 bits. The first bit is a sign bit. It's kind of like how do you represent numbers normally. But here there's a sign bit, an exponent bit, and a fraction. So how the number is computed is first you multiply the sign bit, exponentiate the sign bit by exponentiate -1 by the sign bit times 1 plus the fraction times 2 exponentiated by the exponent minus 127. You don't need to like remember this. This is just for how to understand how this is. There's more of a intuitive explanation of this. The exponent here represents the range of the numbers that you're representing. The fraction or the mantissa represents the precision of the number. So the more bits you assign to the range, the more wider the range of numbers you can represent. The more bits you have at the precision there. Here you're using 23 bits. The more precise you can get the numbers. Like for example, this is just a 4-bit number with 1 exponent and 2 range. So you can only represent numbers from 0 to 3.5, but with a very high precision. All the black dots are the numbers that you can represent. If you kind of increase the range here, you're using 2 range bits. You can represent a larger range right here from 0 to 6, but you can only represent it with a lower precision. There's obviously a trade-off here. If you do this 3 and 0, you can represent a much larger range, as you can see. But you're paying the cost of losing precision. In practice, there's like different ways that people represent the numbers. For example, FP32, you're using 8-bit exponent and 23 bits for the fraction. In FP16, which is the most commonly used precision right now for training these large models, you are using the 5-bit exponent and the 10-bit fraction. Google actually give this BF16 because they think that the range is much more important than the precision, which is actually true because what quantization does is that you're losing some of the precision there. And since the range is more important, it uses more bits for range and less bits for the fraction. And it's actually the same amount of memory, but it gets slightly better performance than using just plain FP16. And if you only use 8 bits here, you're using 4 bits for the 4 bits for the fraction and 3 bits for the mantissa here. You have 4 bits for the exponent and 3 bits for the mantissa. So much about how floating point numbers. Any questions here?
So during the step of like batch normalization or something where the number goes to small as 1, so I suppose in this case precision would be more important than range because the range would be relatively constrained. Would that be of a consideration to what kind of number is used or not?
There are certain cases that precision is important, but when you're like this is mostly during training. I think if you don't need to do training, if you only need to perform inference, like the precision matters less than the range. But you're doing training, a lot of times precision matters, and especially when you're doing the optimizer updates, precision really matters. So that the optimizer states. The atom optimizer states the momentum that you're using uses like the full FP32 representation.
So there's choices of the one.
There's very intricate choices of what precision you want to use in every single detail in the training, and there's like people working on that, engineering, a lot of engineering. That's quantization, representing number using a discrete set. So instead of using like just the continuous numbers, so every weight is actually continuous. You're using kind of a discrete set to represent the continuous numbers. This is all about quantization. What is quantization is about mapping inputs from a large set, which is a continuous signal in the blue line there. And you're mapping it to the, in this case, the nearest, I guess, integer to the dashed lines. You're losing some sort of precision. There's an overview of quantization methods, but today I'm going to only focus on the third part because the first two parts are not used in like modern large language models quantization. Only the third one is actually used in like right now quantization of large language models. This is called linear quantization. What you do is that you do a affine mapping, which is like a linear mapping with a bias here. This is called the 0 point. And how the 32-bit float, like this is the wave matrix, assuming this is the wave matrix, and this is the quantized wave matrix. You're actually like adding like a bias to the quantized wave matrix times a scale, and you recover the full wave matrix. But you can see that here, when you're doing this recovery, you're losing some sort of precision, right? The recovered numbers are not the same as the original numbers. So whenever you do quantization, you're actually losing some information. But later we will see that in practice, the loss of the information there are not really harming the model that much. That's why that quantization is the most, I guess, practical way of making these large models smaller. So how to find these numbers? Like if you represent the floating point numbers by R, the integers by Q, the 0 point by Z, and the floating point like the scale by S. How do you do this? Is that you want to map the floating point range from R min to R max. This is the range. The minimum number of the floating point numbers that you want to represent, the maximum number of the floating point numbers that you want to represent. To like a fixed, this is the quantized, the red one are the quantized, which is only 1, 2, 3, 4, 5, 6, 7, 8 numbers. Discretized, and you want to do this mapping. So you know that this is just some simple derivations. R max equals to S times Q max minus Z, and you do some and you can derive the scale from this. Right? This is just simple math. And deriving 0 point, you use the S to derive the 0 point. This is also simple math. So this is how you derive the scale and the 0 point of quantization in linear quantization. So in practice, people don't do this like a very expensive derivation. People utilize some sort of the weight distribution. So this is what I plotted, the weight distribution of the first convolutional layer in ResNet 50. You can also plot the weight distributions, which is the parameter distributions of the large language models. It's also pretty similar to this. Mostly are centered around 0. And you can see the largest number is 1 roughly over 1. Smallest number is roughly minus 1.5. So it's not totally symmetric, but it's roughly symmetric. So people say that it's mostly centered around 0. So instead of like doing this R max minus R min, they just say R min equals 0, and they just do this derivation. This is most commonly used in modern quantization libraries that they don't do this full derivation.
In practice, is the largest floating point actually used for RMAX, or do they try to cut off the outliers that they get?
I think we'll talk to that later. The outliers are actually pretty important. So let's see here, this is the 1.0, this is the outlier, it's much over the weight distributions. But if you kind of remove the outlier, it harms the model by a very significant margin. So the outliers of the weights are actually the most important. Any other questions here?
So based on this linear quantization, I think we are distributing our resources buckets kind of uniformly across this range. And if the weights are centered around 0, that would basically mean that that's where we should have the highest precision, and everything in the middle, we don't have to be as high precision. Maybe you're gonna talk about this in a few slides.
I don't think I've covered this, but this is a question that I also thought about. So in this example, the quantized numbers are always evenly distributed. But what if you can make the quantized number non-evenly distributed? You can make it centered around 0 more often, and you can make it a larger and smaller number, like more large and more smaller, to represent a larger range. And this is, I think, better than the standard way that people are doing this quantization. But I don't think anybody has done that. I think it requires a lot of like engineering in order to do this sort of how centered you want this to be, how large you want to be the larger and the largest and the smallest. You need to find like a way to do this. But here this is very simple and it actually incurs very minimal performance drop. But I agree with Daniel that if you kind of harness the distribution of the quantized code book in this case, you can kind of get better representation of the weight distribution. So after this is just the basics about how do we do quantization. Next, we are going to talk about 2 very practical methods of post-training quantization. Is that after you train the model, you quantize the model and you perform inference. How do you do this? Before we get into that, any more questions about the basics? Because in order to understand everything afterwards, you need to understand how the quantization works. Great. So the biggest challenge in quantizing large models is that there exists many outliers in these activations. So let's say this is an illustration of activations of the first layer. There are 32 output channel indices. In BERT, there's 768 these output channels. This is only 32, but you can see that the outliers only exist in certain channels, right? Like for example, in channel 5, there's like outliers that's over 50. In channel 30, there's outliers that even like exceeds for 50 or exceeding 75. So outliers exist in these certain channels, and they pose like a great challenge to the quantization. I think to be more explicit here, outliers would make the Rmax, the number Rmax there, very, very large. And if you want to quantize like a 15.1, 0.02, 1, and 0.01, if you want to quantize this with a linear mapping, it gets quantized to 127, 1, 0, 8, and 0. So everything under 0.05 gets mapped to 0. This is also something that we talked about. We are using a fixed codebook to represent everything. So if one number is very, very large, you get losing a lot of precision like here. So everything under 0.05 gets mapped to 0. You're losing too much information here. But the solution is also pretty simple. The outliers I've mentioned only exist in these certain channels. In this case, there's only 32 channels. In BERT, there's 768 channels. You can separately quantize these channels and the other channels actually. So for example, in these channels, you can use a large number, but for the other channels, you can still use the small number for the Rmax. So the solution is called per channel quantization, or called row-wise quantization. It's introduced in the paper that I showed here. This is from like a computer vision paper, but it's actually commonly used right now. Like if you do a per tensor quantization, you're quantizing the entire weight matrix. But if you're doing the per channel quantization, you're only quantizing the first channel. You're using the Rmax of the first channel rather than using the Rmax of the entire weight matrix. Here, this is the or to be more explicit, this is the original weight matrix. After you quantize with the largest number, which is 2.09 here. But when you're doing the per channel quantization, you're not using the two. Actually, the largest number is 2.12. Sorry. But when you're using this like per channel quantization, you're using the 2.09 here, 2.12 here, 1.92 here, and 1.87 here. You're using like a more fine-grained version of quantization, and then it actually incurs less error. Okay.
Can you talk about what you mean by per channel? Like, how does that compare to single layers weights?
So everything here, this is a weight matrix, right? This is one channel, the second channel, the third channel, and the fourth channel. When you're doing this original quantization, you're quantizing the entire weight matrix. You're using the largest number in this entire weight matrix to quantize every channel. But after you do this per channel quantization, you're using the largest number in each channel. And as I've just mentioned here, so in normal, what you do is that you use the largest number there, right? This is over 75, maybe like 90 sort of thing, to quantize everything. To as the maximum number to quantize everything. But after you do this per channel quantization, you're only using the larger number at channel, I guess, 30. But for the other like smaller channels, you're using the standard quantization of the largest number. So you don't lose this precision in the normal channels. You're losing a lot of precision in the outlier channel, obviously.
So that means like by doing that, your every channel have a different precision just based on how large your range of that channel is. Would that introduce problems or like biases towards certain channels because of the precision differences?
Every channel has the same amount of bits. So there's no precision, like a difference. For example, if you're doing 8-bit quantization, each channel is still represented in 8 bits. It's only the codes are different,
Like
but the bits are the same.
so you restore it within the models, the like range can to restore to be farther like deviating from the original number.
That is true. For these like channels with the outliers, the restoration would incur larger error. But you're actually saving a lot of the things, right? Previously, you're losing every like precision in every channel. But right now you're only losing precision in these large activation channels.
Would that introduce any bias towards certain channels or not?
Sorry. I don't think that incurs certain biases. Later we will see that the larger number and the smaller numbers are actually quite important to preserve, and the precision actually doesn't really matter that much. So that's why people originally, like when they're doing this full weight quantization, it works also pretty well, but not that well. But right now, if you kind of keeping the like the larger and the smaller number are more important than saving the precision. Later we will see that. Okay.
Not really familiar with the concept channel here.
You can think of it as dimensions. So in BERT, there's like 768, right? Each word is represented by like a 768 dimension vector. Here the dimension here means channel. This is I guess used a bit confusingly. But the term for like quantization people, they use the term channel. For NLP people, we use dimension more often. I don't know if that answers your question.
Yeah.
Okay. Yeah. So like the outlier features actually significantly degrades performance after quantization. There's a lot of outlier features that I mentioned before, and what this people actually have find this phenomenon for a very long time is that the outlier features significantly degrades the performance after quantization. So like let's get a better understanding of these super large like activations in these large models. It emerges like when the model gets larger. So the number of outlier features gets larger and larger when the model gets larger. Here on the x-axis, this is the number of parameters, and on the y-axis, this is the number of outlier features. And as you can see, as the model gets larger and larger, the number of outlier features also gets larger. Actually, the y-axis is the percentage of outlier features. So this is actually normalized. You can see that there's like a huge jump between like when there's 6 billion parameters to 8 billion parameters. And the emergence of these large features corresponds to a decrease in perplexity, which intuitively it means that these large features are actually helpful for model training, or is actually responsible for most of the gains that we comes from the scaling of these models. That these large features are very, very important. The magnitude of these large features also gets very, very large. It's not only the number of them gets more, but the magnitude of them also gets very, very large when you're like when this is the perplexity. When you're getting better in performance, when you're passing the performance of 15 perplexity, the magnitude of the larger feature gets suddenly super, super large. And you can see that these large features are actually responsible for the amazing performance of these large models. So we really want to preserve these large features when we're doing this quantization, because preserving them means that you can save the model your performance after you do the quantization. So this is what people do here, is that we only quantize the regular activations to 8-bit integers, but we leave the outlier activations as 16-bit floats. So we want to preserve the outlier features there. We don't want to quantize it. We want to save it as is, but we only quantize the regular activations. This is what this paper does, is that for example, in the blue values, they quantize into 8-bit integers, but for the yellow ones, they keep it as 16-bit float numbers. This is about a large sort of derivation of it decompose the outliers into small weight matrices and do this matrix multiplication. This is mostly because you cannot perform 16-bit integer, 16-bit float numbers with 8-bit integer matrix multiplication easily. You need to derive customized kernels for that. So that what they do is that they just they group the 16-bit float numbers together, group the 8-bit integers together, and they perform separate matrix multiplication. This is the weight matrix. This is the activations, and this is the weight matrix. And here, this is the activations, the weight matrix.
So what they're doing here assumes that the outliers or these large values in that matrix multiplication, they're aligned around one particular column or row, like all the yellow column there, like all the large numbers, they correspond to the same index. In practice, is that true?
I think in practice here, this is the large numbers are not kind of evenly distributed in the weight matrix. They correspond to a certain channel, as I've mentioned before. So in the large certain dimensions, in a large dimension, maybe dimension number 5, there's super large numbers. Maybe on dimension number 7, there's all super large numbers. In other dimensions, there's no such super large numbers. If every dimension has these large numbers, every dimension needs to be quantized. So this is kind of false.
How do you know which dimension will have these outliers before you train?
You don't pre-compute which dimensions gets quantized how. You compute the quantization on the fly. So after you get the activations, you get, okay, this dimension has a very large number, and you quantize it with less more precision. I don't know if that makes sense to you.
So it's it is done automatically, or it is done like say I trained for 10 algorithms, and we kind of observe it, and then we do the quantization.
Maybe I can write a single line of Python code to answer that for you. Say, for a dimension in like a 1 to 768, if that dimension has like a large number, you quantize it into like 16-bit. Other else, you quantize it to 8-bit. This is what they quantify. They don't average it over multiple peoples.
As if there's like I would imagine like there's a causal relationship between like the large outliers and the performance, or it's just a correlation. I think there's like explanations available for why outliers has contributed so much for the particular increase in performance and yeah.
That is very interesting. Actually, I've thought about the exact same question as you. I've performed my like like I'm interested in this, so I actually performed some simple experiments of removing these very large outliers, and it can actually incur very heavy performance drop. This is what I found. On the second question, the reason why these outliers are so important, I don't know why. I really don't know why these large outliers emerges and corresponds to like performance that much. I think it's kind of related to the Adam optimizer as well. Since if you train it with SGD, there's the outlier magnitude of the outlier does not get as large as this. So how Adam optimizer works is that you aggregate a lot of the gradients before, so the outliers gets larger and larger. That may be one of the reasons, but what I talk here is not like a scientific conclusion, it's just my intuition. So do you have any questions? Here, this is from the paper, there's like C4 validation perplexities. You can see that across different model sizes, their method works very, very well. Especially like with the smaller models, they actually pretty outperforms the baseline, which is weird to me. But it actually incurs very minimal performance drop. You can see that the performance of the larger model doesn't really drop compared to the full 32-bit. So you're actually representing a number from 32-bit into an 8-bit number, but you're still not losing any performance. But this is just one type of like complexity. I think people that doing quantization does not really validate them on downstream performance that much. They only validate on like the upstream language modeling perplexities, which is one of the limitations of quantization. Post-training quantization. So before the LM-int8 we're talking about, is about quantizing both weights and activations. By activations, I mean when you're doing the forward computations, the output of the model, output of each layer. Before we're quantizing both weights and activations, but later we will see that if you quantize only the weights and leave the activations as is, because the activations has a lot of outliers, but the weights that has less outliers in them. So it's faster with the same performance. But the reason why people first like investigated quantizing both weights and activations, I think it's because it requires a specialized CUDA kernel in order to perform mixed precision matrix multiplication. But if you quantize both, you can use the available CUDA kernels to perform like the same precision matrix multiplication. This is a bit of preliminary how people perform this weight only quantization. You don't need to understand the math. The intuition is just that you first find the weight that when quantized induces the least error, and you quantize it. And then you update the other weights to compensate for the error. The error here is actually computed by like you pass some data into it, and you kind of measure the difference between the activations when quantized and non-quantized. So you're actually needing some data in order to calibrate for this error. This is actually a very old method from 1990s by LeCun et al. But it's actually pretty much, this is very slow because if you have like 100 billion parameters, you can first find the exact parameter when quantize induces the least error and quantize it. and update other weights. This is a very tedious procedure, and it's not very applicable to modern like large language models. But what they find is that they instead of greedily picking the optimal way to quantize, you can actually quantize the weights in any order, and this is actually roughly similar. So you quantize the weights column by column instead of like single weight by single weight. The observation too is that the rounding of the column is only affected by the final update on this column. So instead of performing the like when you quantize a column, you need to update all the other columns, right? So in this case, if they found that when they quantize the weight, they don't update all the other columns. They only update a fixed number of columns and save the updates of the other columns to later iterations, because the final weight is only affected by the final update of that column. I think there's like a illustration of this. In this case, you're only quantizing a fixed number of weights, and you're only updating the columns in this fixed window. You're leaving all the other weights like intact. But after you finish quantizing everything, you update. You do this final update on this column, and this is called kind of lazy updates, only on a subset of the weights. You don't need to have like a very detailed understanding of this. If you're interested, you can refer this to this very recent paper. Not very recent, it's 1 year ago. This is their experiment results. RTN means that you round to the nearest, which is roughly what LM int 8 does. You can see like if you only quantize the weights, like it's rounding to nearest, it's not very good sometimes. But if you're quantizing the weights and columns both, and this actually works pretty well in both 4 bits and 3 bits. Before we were using like 8-bit quantization, but this actually works pretty well for even 4 bits and 3 bits. And it actually incurs very minimal performance on larger models. So so much about quantization. Is there any questions about quantization here? Okay. Okay, I guess class is over.